All right, so I wanted to cover this really short amount of time, the simple pendulum, because it's another example of a simple harmonic oscillator. So a simple pendulum is just a mass suspended by a string, and we deflect it some angle, and when we let it go, it swings back and forth. In a perfect world, it'll swing back and forth forever. So some of the terms that we would define for our pendulum are the length of the string, which is right here, the angle that it's deflected, theta, and this x right here is measuring along the arc. So that's sort of like its displacement in a way. So we're actually going to work with displacement in terms of the angle and also in terms of x. So we do a force body diagram of this mass that's hanging by the string, and the two forces that are acting on it are the tension and its weight. And we want to look at this in terms of radial and tangential forces, because it's basically moving in a part of a circle. And so we're breaking down our forces into components. So instead of doing x and y, we're doing forces that are along the radial direction, along the radius, and then also tangential. Now the tension is strictly in the radial direction, goes in towards the center, but the weight actually has two components, and so mg cosine is going to be the radial component of weight, and mg sine is going to be the tangential component of weight. So we're going to work with the forces that are in the tangential direction, producing a tangential acceleration. So the only force that we have is mg sine of theta. And we're going to make it negative because this is going to be the positive direction, because it's the direction of increasing x. And if you think about it, as we're looking at it, this is a restoring force. It's trying to bring the pendulum back down to the bottom, which is in the equilibrium position. And as the pendulum continues to swing this way, the weight will push it back again down towards the bottom. So that component of the weight is the restoring force in this problem. And so since x is our variable along the arc, that's how we're going to write our tangential acceleration. Now, when we look at this, we have a little bit of an issue with variables, because on this side, theta is our variable, but on this side, x is our variable. And so somehow we have to bring those together. We need to write everything in terms of one variable. But what we can do is x is like the arc is equal to L times theta. So this is the length of the string. And so this is kind of like r theta, except instead of radius, we're writing the length of the string. And so dx dt is going to be L d theta dt, because the length isn't going to change, and d squared x dt squared is going to be L d squared theta dt squared. So what we can do is we can substitute this expression right here in for the acceleration. And that's going to allow us to write everything in terms of one variable. All right, so now we have everything in terms of theta, which is a help. Mass is going to cancel out, so it doesn't matter how much mass is at the end of that pendulum. And if I rearrange this to write just in terms of this, the acceleration is equal to, I get minus g over L times the sine of theta. Now, remember that our previous expression was that we did simple harmonic oscillator. Was that we just had the variable here. We didn't have the sine of theta. And this is where we come up with the small angle approximation, which is talked about right here. You might remember at some point in calculus, they talked about the series expansion for the sine function and the cosine function, where you could write this as a series of powers of theta. And if theta is small, the higher powers of theta become really small because you're cubing it and you're taking it to the fifth, etc. And so we can sort of neglect everything else and just say that when our angle's small, we can approximate the sine of theta by theta, which would change our expression to and now it has the form that we would expect. Now, what do we mean by small? We mean an angle less than 10 degrees, but you can test this on your calculator, but if you use theta equal to something less than 10 degrees, but you put it in radians, you can see that this is true, that the angle in radians will be about the same as the sine of that angle in radians. So our expression that we got, our equation of motion for our pendulum, looks like this, which means that our omega is the square root of g over L. And that's 2 pi f, or 2 pi over period. So our period is equal to 2 pi square root of L over g. So you have a lot of problems for the pendulum talking about how basically the period can be affected by either the length of the string or the acceleration of gravity at that location. I think I just have one more slide. It just sort of summarizes this material. And I think that's about it. That should cover it for pendulums. Hopefully that makes some sense.